Hey everybody, let's talk about expected values and things. And what I thought I would do is go through some of the stuff that we did last Wednesday and talk about it in a little more detail. And I'll probably have to stop at a certain point. I think it only lets me do 15 minutes at a time, but maybe I'll be able to bang through it in 15 minutes. Who knows? Okay, so let's take a look at continuous probability density functions. We're going to look at continuous random variables. So I'm going to have a random variable x, and it has some probability density function f of x. Then I know that for any particular value of f of x, it's always between 0 and 1. And it can take on the values at the endpoint 0, and it can take on the values 1. Okay? And to calculate a probability, it's always over an interval, and we talked about that a little bit. You don't take it just at a point, it's always over an interval. As we know, our ultimate is if I run from minus infinity to infinity, of that, it goes to 1 by definition. Okay? So, that being said, if I have some constant a times a probability density, and I see I missed my dx's, well, we'll just pretend that they're there. I can push that a to the outside, and if I integrate f of x, then I have the integral of a probability function, but I know that's just 1, so I have a times 1, which is a, and there's nothing wrong with that. Okay, gosh, I did it all the way through. Great. All right. So anyhow, I know by definition that the integral of x times f of x is the expected value of x, or mu, as long as the absolute value of x times f of x, that integral is finite. And don't worry too much about that, that's just the definition. Obviously, if I'm leaving off the dx's, I'm not going to split hairs over the definitions too much. Okay? Then the next one, if I have the absolute value of some h of x, f of x, if that's finite, then the expected value of h of x is that h of little x times f of x dx, the imaginary dx, invisible dx. And if I integrate that, that gives me the expected value of h of x. Okay? And that's that law of the unconscious statistician that I mentioned. Okay? So that's good for one variable. And notice on this one, let me back up a minute. This is good if you have stuff like constants and stuff, or something like 3 plus 4x, or 2 times x. You don't mix variables. In this one, you only have one variable at a time. So what you do next is, if you have multiple variables, if you have x and y, and you have a joint probability density function, f of xy, and you've got that absolute value thing in effect, oh, there's my dx dy, and it's finite, then the expected value of h of xy takes on this definition. Okay? But I don't want you to get too choked up about the integration. These are just definitions. I want you to be able to work with the definitions of the expected values, not so much the integration, but with these rules. Okay? So, if I have the expected value of ax plus by plus c, I know that that is equal to a times expected value of x plus b times the expected value of y plus c. All right, well, how does that work? Well, the expectation operator is a linear operator. So that means I can work on each term individually. So I'm going to have e times a of x plus e b of y plus e of c. All right, if I have this, the first term, I can push the constant through. So I have a times the expected value of x. Aha, that's just all I need. Plus b times the expected value of y. Same thing. Expected value of a constant is just the constant. That's all you have to do. Now, if you can do this, that's all no pun intended, that's all I expect you to be able to do. All right? So now, definitions of variance, there's two of them. You can either use the expected value of the quantity x minus the expected value of x, the whole thing squared, or you can use the expected value of x squared minus the expected value of x, the quantity squared. Okay? Either one's fine, whichever you feel the most comfortable with. So let's look at some properties of variance. Variance is always greater than or equal to 0. We saw that the other day because every term in it is squared, so it has to be greater than or equal to 0. And let's talk about our very favorite proof. So we know that the variance of a plus b squared is going to be equal to b squared variance of x. All right? And if I were a student, and I am, I would know how to do that. Because this is going to rear its ugly little head on the midterm. Woo. All right. So to solve this, or this is a way to solve it, what I did was take the second definition, okay? And I attacked it by I did the second piece first. I did the expected value of a plus bx. So I know that's going to be e of a plus e of bx, and that's going to give me a, plus b times e of x. So that's the expected value of bx, or a plus bx. But I have to square that term. Okay? And just when I square it, I get a squared plus 2ab expected value of x plus b squared e of x, the quantity squared. And I put a couple little stars next to it. We're going to come back and use that in a little bit. Okay? Now, I'm going to take the first section. Let me scoot back for a minute. So I need to take x, the quantity squared. So the x is that first stuff in here. Okay? So that would be like your h of x. All right? So I need to square this whole piece before I use the expectation operator. So that's going to be a squared plus 2abx plus b squared x squared. So you can do the FOIL or whatever method you use. Now you apply your expectation operator. So you've got e of a squared plus e of 2abx plus e of b squared x squared. Okay, so you apply that, you've got a squared plus 2ab e of x plus b squared e of x squared. All right, so that's your first piece. Now you have to put everything together. So here's the stuff from the first, and you've got to subtract off the stuff from the second. So I put the stuff in the second in the curly braces. That's the stuff from the starred piece. So here's all the stuff from the first. And I'm going to subtract off a squared minus 2ab e to the, expected value of x minus b squared e to the x, the quantity squared. But the a squares drop out. The 2ab expected value of x drops out. And I'm left with b squared ex squared minus b e to the x, the quantity squared. But if I look at these expectation terms, that's just the definition of variance. So all I have is b squared times the variance of x, which is what I wanted. Cool, huh? I mean, and that's the kind of stuff I want. I don't want you to worry about integrating or anything like that. Okay? All right. Let's take a look at if x and y are independent, then the variance of x plus y is equal to the variance of x plus the variance of y. The general case, if they are not independent, then you have the variance of x plus the variance of y plus 2 times the covariance of x plus y, where the covariance is the expected value of x minus mu of y, my fault, x minus mu of x times y minus mu of y. Or the second definition, expectation of x times y minus mu of x times mu of y. Okay. Now let's look at some of the properties of covariance. If x and y are independent, then the covariance of x and y are 0. The covariance of a plus bx, c plus dy are b times d covariance of x and y. The covariance of x plus y, comma z is equal to the covariance of x and z plus the covariance of y and z. The covariance of x and x, that is the covariance of x with itself, is just equal to the variance of x. And you'll see how that works a little bit later when we get into some of the time series where the time is itself. When you have the time series, or excuse me, the time period, say, like 3 and 3, say. And then the covariance of x and y is equal to the covariance of y and x. And we are going to make it for 15 minutes. Great. All right. The definition of correlation, essentially what you're going to do is take the covariance and divide it through by the variance of each of the variables. Correlation works at 2 variables at a time. And we know that the correlation goes from -1 to 1. It's very handy. A couple of general case remarks. The variance of a and x is always a squared times the variance of x. It just is. Accept it. I can prove it to you, but I know you're sick of proofs. The variance of the summation of ai times x is equal to the summation of the ai squared variance of x. And since the variance of x is going to be some constant, you pull the variance of x out times the summation of the ai squared. And finally, if you just have the covariance of ax, by, you're going to have the variance, a squared times the variance of x plus b squared times the variance of y plus 2ab covariance of xy. Okay? Hope this helps. Thanks.